Imagine you're Enrico Fermi. It's December 2nd, 1942. You're standing in a converted squash court underneath the bleachers of Stagg Field at the University of Chicago. The ceiling is low. The air smells of graphite dust and something metallic that settles in the back of your throat. In front of you is a pile of uranium and graphite blocks stacked 20 feet high. It took 49 days to build, 57 layers of carefully arranged blocks, each one placed by hand, each one heavier than it looks. Nobody on Earth has ever done what you're about to do. And if it goes wrong, if the chain reaction doesn't stop when you need it to, the safety system is 3 men standing on a balcony above you holding buckets of cadmium solution ready to pour. That's it. 3 men. 3 buckets. You are about to start the world's first controlled nuclear chain reaction, and the backup plan fits in a hardware store. Here's what most people don't know about that morning. Fermi wasn't nervous. Not visibly. The people who were there later described him as calm, almost cheerful, moving through the room with the quiet confidence of a man who had done the math so many times he already knew the answer. He was 41 years old. He had already won the Nobel Prize 4 years earlier for his work on neutron bombardment. He had fled fascist Italy with his wife Laura after the ceremony in Stockholm, turned left instead of right, and ended up in America instead of Rome. He had been building toward this moment for years. The team around him that morning was 49 people. Physicists, engineers, graduate students. Some of them understood exactly what they were doing. Some of them understood pieces of it. All of them had signed secrecy agreements that meant they couldn't tell their families where they worked or what they were doing there. Laura Fermi didn't know. She thought her husband was doing war research. She was correct, in a way. The reactor they had built, they called it Chicago Pile 1, which is perhaps the least dramatic name ever given to a world-changing object. Worked on a principle that was only 4 years old, 4 years earlier. In December 1938, 2 chemists in Berlin had split a uranium atom for the first time and produced barium as a result. The physicist Lise Meitner, working in exile in Sweden, had received a letter describing the result and spent a Christmas walk in the snow working out what it meant. The uranium nucleus had split in half. And when she calculated the energy released by that splitting, the number matched an equation that Albert Einstein had written down 33 years earlier. An equation most people had assumed was theoretical, a curiosity, something that described the universe in principle but couldn't be made to do anything useful in practice. E equals mc squared. Mass times the speed of light squared. The speed of light is 300 million meters per second. Squared. That number becomes 90 quadrillion, which means a tiny amount of mass contains an amount of energy that makes the word enormous feel inadequate. Meitner understood this immediately. So did every physicist who read her paper. So did the governments of every major power on Earth. Within months, the question was no longer whether it was possible to release this energy. The question was, who would do it first? By 1942, the answer to that question had become the most important secret in the world. The Manhattan Project, the American program to build an atomic weapon, was already underway. Sites across the country, thousands of workers who didn't know what they were building. A budget that would eventually reach $2 billion. But before anyone could build a bomb, someone had to prove that a chain reaction could be sustained. A bomb releases its energy in a fraction of a second. An uncontrolled, instantaneous chain reaction. But to understand how to build that, you first had to understand how to start a chain reaction and keep it running. Slowly, deliberately, under control. That was what Fermi was doing in the squash court. At 9:45 in the morning, the experiment began. Fermi stood at a balcony above the reactor with a slide rule, a physical calculating device, because there were no computers in 1942, or at least none that could do what he needed, and directed the removal of the control rods. The control rods were long cylinders of cadmium, a material that absorbs neutrons. While they were inserted into the reactor, they prevented the chain reaction from starting. Pulling them out, slowly and in careful increments, allowed neutrons to begin striking uranium atoms. Each time a uranium atom was struck and split, it released energy, and it released more neutrons. Those neutrons could strike other uranium atoms, which would split and release more neutrons, which would strike more atoms. This is the chain reaction. Each step triggers the next. Each split makes the next split more likely. The Geiger counters around the room began to click, slowly at first, then faster. Fermi watched his instruments. He called out numbers. He ordered the control rods pulled out by another foot, another 6 inches, another foot. The clicking accelerated. At 2:00 in the afternoon, he called a lunch break, not because anything was wrong, because it was lunchtime. And Fermi believed in lunch. The chain reaction was controlled, the instruments were reading correctly, and the sandwiches were ready. This detail, the lunch break, is one of the things that makes Fermi unusual. While other physicists were electric with anxiety, Fermi ate his sandwich. At 3:25 in the afternoon, the experiment resumed. The final control rod was pulled to its critical position. The Geiger counters did not just click, they screamed. So fast. The individual clicks blurred into a continuous sound, a rising mechanical shriek that filled the concrete room. The chain reaction had gone critical. It was self-sustaining. Uranium atoms splitting, releasing neutrons, which split more atoms, which released more neutrons. The reactor was running on its own. Fermi let it run for 28 minutes. Then he ordered the control rods reinserted. The clicking slowed. The screaming dropped back to clicks. The clicks became sporadic. The reactor stopped. The room was quiet. George Weil, One of the physicists present later said that the moment felt anticlimactic. No explosion, no visible light, no drama, just instruments changing their readings in a cold concrete room under a football stadium. Someone opened a bottle of Chianti, Italian wine, a nod to Fermi's origins, and passed it around. They drank from paper cups because no one had thought to bring glasses. Herbert Anderson, one of the younger physicists, signed the bottle's straw, wrapping with the date and the words, "The Italian navigator has just landed in the New World." The New World. That's what they called it among themselves, not the atomic age. The New World. What they had proven. That afternoon, in 49 days of construction and 28 minutes of operation, was not yet a weapon and not yet a power source. It was a proof, a demonstration that the chain reaction was real, controllable, and reproducible. The weapon would come 3 years later. The power plant would come 9 years after that. But everything, the bombs, the reactors, the submarines, the power plants, the long complicated argument about nuclear energy that the world is still having today, everything traces back to that squash court, to those 49 people and their paper cups of Chianti, to a man with a slide rule who stopped for lunch because it was lunchtime. Here's the thing about nuclear energy that the next few hours are going to show you. It is not one story. It is at least 4 stories happening simultaneously. A physics story, an engineering story, a political story, and a moral story. And they have been tangled together since that afternoon in 1942, in ways that have never fully been separated. By the time we're done tonight, you'll understand how a reactor works. You'll understand what actually happened at Chernobyl and Fukushima and why. You'll understand the argument that's happening right now between the people who think nuclear energy will save the world and the people who think it will end it. And you'll understand why the answer, like almost everything in this story, is more complicated than it first appears. Let's keep going. Imagine you're Ernest Rutherford. It's 1909. You're in a laboratory in Manchester, England, and you've just handed 2 of your students, Hans Geiger and Ernest Marsden, what sounds like the most boring experiment in physics. Take a piece of gold foil. Make it as thin as you can, thinner than that. Keep going until it's only a few hundred atoms thick, so thin you can almost see through it. Now fire particles at it, small particles, alpha particles, the kind that come off radioactive materials, tiny and positively charged, moving at about 15,000 kilometers per second. Fire them at the gold foil and see what happens. Rutherford expected almost nothing to happen. The dominant model of the atom at the time, proposed by his own mentor, J.J. Thomson, described the atom as a kind of pudding. Positive charge spread evenly throughout, like a cloud, with electrons embedded in it like raisins. A diffuse, spread-out thing. If that model was right, the alpha particles should pass straight through the gold foil, maybe deflecting slightly, the way a bullet passes through fog. A little resistance. No drama. What actually happened changed physics forever. Most of the alpha particles did pass straight through, but some of them bounced back, not deflected, not slowed, bounced straight back the way they came, as if they had hit something solid. Rutherford later said it was the most incredible event of his life, as if you fired artillery shells at tissue paper and they came back and hit you. He spent 2 years working out what it meant. The answer he arrived at in 1911 was this: the atom is almost entirely empty space. Almost all of its mass, more than 99.9% of it, is concentrated in a tiny central nucleus, almost unimaginably small compared to the size of the atom itself. Here is how small. If you took a hydrogen atom and expanded it until it was the size of a football stadium, the full stadium, from end zone to end zone, upper deck to playing field, the nucleus at the center would be the size of a marble sitting on the 50-yard line. Everything else is empty. The electrons orbiting the nucleus are so small and so far from the nucleus, relative to the size of the atom, that they barely register. The atom is almost nothing, almost pure void. The marble in the center of the stadium and a few specks of dust orbiting it at the upper deck. And yet, and this is the thing that makes the atom remarkable, that marble, that almost invisibly small nucleus, contains almost all the mass and almost all the energy. By 1932, physicists had worked out what the nucleus is made of. 2 types of particles: protons, which carry positive electric charge, and neutrons, which carry no charge at all, electrically neutral, which is where they get their name. Protons and neutrons are packed together in the nucleus with a force that has no name in everyday language because it operates at scales too small to experience directly. Physicists call it the strong nuclear force. It is the strongest force in nature, far stronger than gravity, far stronger than electromagnetism, but it only operates across distances smaller than a nucleus. Step outside that range by even a tiny fraction, and it simply stops working. This is why the nucleus is simultaneously stable and explosive. Inside the nucleus, the strong force holds everything together with enormous power. But if you can get a neutron inside the nucleus of certain atoms, uranium specifically, the nucleus becomes unstable. It wobbles, and sometimes it splits. When it splits, the 2 pieces fly apart, driven by the electromagnetic repulsion between their positive charges. Charges that the strong force had been overcoming as long as the nucleus was intact, but that the strong force can no longer reach once the nucleus has divided. The energy released in that split is the energy that had been stored in the strong force binding the nucleus together. That energy is nuclear energy, and the reason it is so much larger than any energy released by chemical reactions. Burning coal, exploding dynamite, anything you encounter in everyday life is that the strong nuclear force is so much more powerful than the electromagnetic and chemical forces that govern everything at the scale of human experience. A chemical reaction rearranges electrons between atoms. A nuclear reaction rearranges or splits the nucleus itself. The nucleus is smaller than the electron cloud by a factor of roughly 100,000. The forces involved are proportionally stronger. This is why a kilogram of uranium fuel contains roughly 3 million times more energy than a kilogram of coal. Not 3 times, not 100 times, 3 million times. The element that makes all of this practical is uranium. Uranium is the heaviest naturally occurring element on Earth. It was discovered in 1789 by a German chemist named Martin Heinrich Klaproth, who named it after the planet Uranus, which had been discovered 8 years earlier. For most of the century after its discovery, uranium was used as a yellow pigment in ceramic glazes. Uranium glass. Glass with small amounts of uranium added glows green under ultraviolet light and was fashionable. In the 19th century for decorative objects, nobody suspected it was radioactive until 1896, when the French physicist Henri Becquerel left a uranium sample sitting on a wrapped photographic plate in a drawer. He was waiting for a sunny day to run an experiment and found that the plate had been exposed anyway. The uranium was emitting something invisible that could pass through the wrapping and affect the plate. Becquerel had discovered radioactivity, more or less by accident, because it rained in Paris for a week. Marie Curie, working with her husband Pierre, took Becquerel's discovery and made it into a field. She coined the term radioactivity. She discovered 2 new elements, polonium and radium. She won 2 Nobel Prizes in 2 different scientific disciplines, and she did it while facing the kind of institutional barriers that would have stopped almost anyone else. She also died of aplastic anemia in 1934, almost certainly caused by decades of radiation exposure from handling radioactive materials without protection at a time when no one fully understood what radiation did to the human body. Her notebooks are still radioactive. They are kept in lead-lined boxes in the Bibliothèque Nationale de France. Researchers who want to examine them must sign a waiver acknowledging the radiation risk. By the time Fermi stood in that squash court in 1942, physicists had been studying the atom for 45 years. They knew what it was made of. They knew it was mostly empty space. They knew the nucleus was unimaginably dense and small. They knew that certain nuclei were unstable and could be made to split. What they had just proven in that 28-minute experiment with the Geiger counters and the paper cups of Chianti was that the splitting could be controlled, that you could start a chain reaction and stop it, that the energy inside the nucleus was not just a theoretical quantity in Einstein's equation, but a real, extractable, manageable thing. The marble in the center of the stadium. All that time, all those centuries of human beings going about their lives, burning wood and coal and oil. The answer to the question of where a better energy source might come from was sitting inside. Every atom of every element in every object in the world, inside the marble. The stadium was empty. The energy was in the marble, and now they knew how to open it. Imagine you're Albert Einstein. It's 1905. You're 26 years old. You live in a rented apartment in Bern, Switzerland, with your wife Mileva and your infant son Hans Albert. You work 6 days a week at the Federal Patent Office examining other people's inventions, checking whether they work, whether they're original, whether the descriptions are precise enough to be protected by law. You are good at this job. Your supervisor says so in his evaluations. You have a talent for finding the flaw in a technical argument, for identifying the gap between what a device is claimed to do and what it actually does. You are not, by any conventional measure, a physicist. You have no university position, no laboratory, no senior colleagues who take your ideas seriously. Your doctoral dissertation was rejected the first time you submitted it. The professors whose recommendations might have opened academic doors found you difficult, too independent, too willing to follow your own thinking rather than theirs. And their letters reflected that. And yet, in the 12 months of 1905, working in the hours before and after your patent office shift, you publish 4 papers that, between them, contain the special theory of relativity, an explanation of the photoelectric effect that will eventually win you the Nobel Prize, a mathematical explanation of Brownian motion that will definitively prove atoms exist. And, almost as an afterthought, in a 3-page paper published in September, a question: does the energy content of a body depend on its mass? Your answer is yes. And the equation you write down to express that answer will eventually be the most recognized equation in human history. Here's the thing about EMC squared that most people don't understand. It wasn't a sudden revelation. It wasn't a moment of genius striking from nowhere. It was the logical conclusion of a line of thinking Einstein had been following for 10 years, since he was 16 years old, and first asked himself a question that sounds almost childlike in its simplicity. What would it look like to ride alongside a beam of light? If you could match the speed of light exactly, if you could travel at 300 million meters per second side by side with a light beam, what would you see? He thought about this for 10 years, not obsessively, not constantly, but the way certain minds hold certain questions, present in the background, return to in quiet moments, never quite let go. The problem was that the question had no good answer inside the physics of the time. James Clerk Maxwell's equations, which described electricity, magnetism, and light with extraordinary precision, said that light travels at a fixed speed. Not a fixed speed relative to something, a fixed speed stated as an absolute value with no reference frame attached. But Newton's physics said that speeds always add. You're moving and you throw something forward. The thing moves at the speed of the throw plus your own speed. If you're in a car going 60 miles an hour and you throw a ball at 30 miles an hour, the ball travels at 90 miles an hour relative to the road. So if light travels at a fixed speed, what happens when you chase it? Do you catch it? Does it slow down? Does it speed up? Maxwell said no. Newton said yes. They couldn't both be right. The answer Einstein arrived at in the spring of 1905, riding a tram away from the clock tower in Bern, watching the tower recede through the window, was that Newton was wrong, not wrong about most things. Newton's physics worked perfectly at everyday speeds and scales. But at speeds approaching the speed of light, something different happened. Time slowed down, space compressed, and mass, the amount of matter in an object, was not fixed but increased as the object moved faster. More than that, mass and energy were not two separate things. They were the same thing expressed differently. Mass was compressed energy. Energy was liberated mass. The equation that expressed this was three symbols: E equals mc squared. E is energy, m is mass, c is the speed of light, approximately 300 million meters per second, squared. That number is 90 quadrillion, which means that even a tiny amount of mass contains an enormous amount of energy. 1 kilogram of mass, completely converted to energy, equals 90 petajoules, enough to power New York City for roughly 2 years. Enough to detonate with a force larger than any conventional weapon ever built. Einstein published this in September 1905. 3 pages, almost no citations. The conclusion stated matter-of-factly at the end, as if it were obvious once you followed the logic. Here's what nobody understood at the time. The equation was correct. The physics was right. But nobody in 1905 had any idea how to actually convert mass into energy. The numbers were extraordinary, but they were theoretical, like knowing the energy content of water without knowing how to build a dam. You could write EMC squared on a blackboard and the universe would nod and say, yes, that's right, that's how it works. But actually extracting that energy, actually reaching into the nucleus of an atom and pulling out the compressed energy stored there, required understanding the atom in ways that 1905 physics hadn't yet achieved. It required discovering the neutron, which didn't happen until 1932. It required discovering fission, the splitting of the nucleus, which didn't happen until 1938. It required understanding the chain reaction, neutrons splitting atoms, which release more neutrons, which split more atoms, which Fermi demonstrated in the squash court in 1942. 37 years between the equation and the first controlled release of the energy it described. 37 years of physics, building on physics, each discovery making the next one possible. None of the people involved entirely sure where it was leading. Lise Meitner is the person who connected Einstein's equation to Hans' chemistry. She was born in Vienna in 1878, the third of 8 children of a Jewish lawyer. She became interested in physics at a time when women were not permitted to attend Austrian universities as regular students. She attended lectures as an auditor, unofficially tolerated but not enrolled, until the rules changed in 1901. She moved to Berlin in 1907 and began working with Otto Hahn, a chemist. For 30 years they collaborated, Hahn doing the chemistry, Meitner doing the physics, a partnership that produced some of the most important nuclear research of the early 20th century. Then 1938. Hitler, the Nuremberg Laws. Meitner was Austrian and Jewish and protected, barely, by her Austrian citizenship, until Germany annexed Austria in March 1938, and that protection disappeared overnight. She fled in July 1938, a small suitcase, 10 marks, the legal limit for Jewish immigrants, a diamond ring given to her by Otto Hahn in case she needed money. She crossed into the Netherlands on a tourist visa and eventually reached Stockholm, where she had been offered a position at the Nobel Institute. She was 60 years old. She was starting over in a country whose language she barely spoke, in a laboratory that had nothing she needed, separated from the work she had spent 30 years building. In December 1938, a letter arrived from Hahn. He and his colleague, Fritz Strassmann, had bombarded uranium with neutrons and found barium in the results. Barium is roughly half the atomic weight of uranium. The uranium nucleus had apparently split in two. Hahn didn't know what to make of it. He wrote to Meitner, his old partner, the physicist, the one who understood the theory, and asked her to help him understand what they had found. Meitner was spending Christmas with her nephew, Otto Frisch, also a physicist, at a small town in Sweden called Kungälv. They went for a walk in the snow, Frisch on skis, Meitner walking, both of them talking through what Hahn's letter described. Frisch later recalled, sitting down on a fallen log to work out the mathematics. Meitner produced a small piece of paper. They began calculating. If the uranium nucleus split in two, the two fragments would be smaller nuclei, and the mass of those two smaller nuclei would be slightly less than the mass of the original uranium nucleus. Where did the missing mass go? E equals mc squared. The missing mass had become energy, exactly the amount of energy Einstein's equation predicted. The calculation matched. They called the process fission, from the Latin word for splitting, the same root as the word fissure, as in a crack, a divide. Frisch went back to Copenhagen and told Niels Bohr, who was about to leave for America. Bohr arrived in New York in January 1939 and told a conference of physicists. Within weeks, laboratories across America and Europe had confirmed the result, and every physicist who understood what fission meant understood something else immediately. If splitting one uranium nucleus released that much energy, and if that splitting released neutrons, that could split more nuclei, which would release more neutrons, which could split more nuclei. The chain reaction. Einstein was in Princeton when he heard about the fission discovery. His first reaction, by his own account, was that he hadn't thought of it. The equation he had written in 1905 had described the energy stored in mass. He had not imagined, had not specifically thought through a mechanism by which that energy might actually be released. Nobody had connected the theoretical equation to the practical physics of the nucleus until Hahn split it and Meitner calculated what it meant. Later, Einstein would sign the letter to President Roosevelt warning that Germany might be developing a weapon based on fission, a letter that helped launch the Manhattan Project. He spent the rest of his life with complicated feelings about this. The equation was just physics. The physics was just true. He hadn't designed a weapon. He had described how the universe worked. But describing how the universe worked had turned out to have consequences. It usually does. The equation is still on blackboards in physics classrooms all over the world. 3 symbols. The most famous equation in history, written by a 26-year-old patent clerk in a 3-page paper as an almost afterthought at the end of the most productive year in the history of physics. It described something true about the universe, something that had been true since the first atoms formed after the Big Bang, something that the sun has been doing for 5 billion years, converting mass to energy every second through nuclear fusion at its core. The universe already knew. Einstein just found the right way to write it down. And once it was written down, the people who read it could not unlearn it. That is the thing about true equations. They don't go back in the box. Einstein's equation sat quietly. For 33 years, a beautiful piece of mathematics that nobody could turn into anything useful. That changed in December 1938 in a laboratory in Berlin when 2 chemists ran an experiment that made no sense. Otto Hahn and Fritz Strassmann had been bombarding uranium with neutrons, a fairly ordinary experiment by 1938 standards. Physicists had been doing this for years, expecting uranium to absorb a neutron and become a slightly heavier, slightly different version of itself. Instead, they found barium. Barium is roughly half the mass of uranium. Elements don't simply turn into completely different, much lighter elements. Nothing in decades of nuclear physics predicted this. Hahn didn't understand what he'd found. He was a brilliant chemist, but this problem needed a physicist. So he wrote to the person he trusted most with impossible questions. Lise Meitner, his closest collaborator for 30 years. There was a complication. Meitner was Jewish. Austria had just been annexed by Nazi Germany, and only months earlier, she'd fled Berlin with almost nothing. A small suitcase, a few pieces of jewelry sewn into her coat lining, in case she needed to bribe her way across a border. She was now hiding in Sweden. Hahn's letter reached her there on Christmas break, in a snow-covered village. Meitner read it walking with her nephew, Otto Frisch, also a physicist, also a refugee. Together, they worked through the numbers. What if the uranium nucleus hadn't absorbed the neutron at all? What if it had split, not chipped, not decayed slightly, split clean in half, like a drop of liquid pulled apart by two hands? They sat down on a log in the snow and did the arithmetic right there. With nothing but a pencil and the back of an envelope, they calculated the mass of uranium before the split. Then, the combined mass of the fragments, barium, and another lighter element, krypton. The two numbers didn't match. A small amount of mass had simply vanished. And that missing mass hadn't disappeared. It had converted directly into energy, exactly as Einstein's equation predicted, back when nobody believed it described anything real. Each single splitting uranium atom, they calculated, released roughly 200 million electron volts of energy. A struck match releases energy through a chemical reaction. Atoms rearranging their outer electrons. A splitting uranium atom releases energy through a nuclear reaction. The atom's core itself tearing apart. Atom for atom, the nuclear reaction released roughly 10 million times more energy. And uranium didn't split just once. When it split, it also released spare neutrons. The very particles that had triggered the split in the first place. Those neutrons could strike other uranium atoms, which split, which released more neutrons, which struck more atoms. Frisch borrowed a word from biology to describe it. Cells divide. This felt the same. He called it fission. From the Latin word for splitting, by the time they finished their walk, Meitner and Frisch understood something no government on Earth yet knew. A chain reaction was possible. And if a chain reaction was possible, then in principle, so was a weapon more powerful than anything humanity had built. Frisch rushed to Copenhagen, to the laboratory of Niels Bohr, catching him just as he was about to board a ship to the United States. Bohr reportedly slapped his forehead and said, "Oh, what fools we have all been." Not because the physics had been hidden. It had been sitting in plain sight for years, buried inside data nobody had assembled correctly, until a woman forced into exile did the arithmetic on a log in the snow. Meitner and Frisch published their explanation in Nature in early 1939. Word spread through the physics community within days, because everyone reading the paper reached the same conclusion. Physicists in Paris began their own experiments. So did physicists in London, Washington, Moscow, and Berlin, where Hahn and Strassmann's laboratory kept working, now under a government that would very much like a weapon like this for itself. The world's leading nuclear scientists, many of them, like Meitner, refugees who had fled Hitler's Europe with nothing, understood a bitter irony. The country most likely to build this weapon first was the one they had all just escaped. Meitner herself was never awarded the Nobel Prize for this discovery. In 1944, the committee gave the prize in chemistry solely to Hahn. a decision still debated as one of the prize's greatest omissions. But in the winter of 1938, none of that recognition mattered yet. What mattered was a single urgent question now spreading from laboratory to laboratory, government to government. If a chain reaction was real, repeatable, controllable, someone, somewhere, was going to try building it into a bomb. The only question left was who could get there first. Word of the discovery was about to reach a quiet house on Long Island, where an old man who had spent his life avoiding politics was about to be asked to sign his name to a letter that would change everything. That letter reached a quiet house on Long Island on a warm morning in August 1939. Papers were spread across a wooden table. An elderly man with untidy white hair leaned forward, reading the carefully worded document one last time before signing his name. The man was Albert Einstein. He did not enjoy politics. He had spent most of his life thinking about light, time, gravity, and the hidden laws of the universe. He never wanted his discoveries to become weapons. But Europe was changing. Germany had invaded neighboring countries. Hitler's government had forced many of Europe's greatest scientists to flee. Those who remained were now working under a regime preparing for war. Discovery had already spread through every major physics community on Earth. The question was no longer whether this energy existed. The question was whether someone could turn it into a weapon. Einstein wasn't the one who actually wrote the letter. That task belonged to a Hungarian physicist named Leo Szilard, who had imagined the possibility of a nuclear chain reaction years before anyone knew it could actually happen. Now, after Meitner's discovery, his fears suddenly seemed real. If Germany developed an atomic bomb first, the consequences could be unimaginable. Szilard believed the United States had to begin its own research immediately. But he needed a name the president would recognize. There were few names more respected than Albert Einstein's. So, Einstein signed. The letter was addressed to President Franklin D. Roosevelt. It warned that uranium could become the basis of extraordinarily powerful bombs, and that Germany had already taken steps to secure uranium supplies in occupied Europe. It ended with a simple request. The United States should begin investigating nuclear research before it was too late. Only a few pages long. Yet, those pages would quietly change the course of history. At first, little happened. Roosevelt received the letter in October 1939. The Second World War had already begun in Europe. Germany had invaded Poland only weeks earlier. Britain and France had declared war. Still, the United States remained officially neutral. Roosevelt listened carefully as his advisors explained Einstein's warning. After a long pause, he reportedly said, "This requires action." Those 3 words marked the beginning of a project unlike anything humanity had ever attempted. It would eventually become known as the Manhattan Project. The name sounds small, almost ordinary. In reality, It became one of the largest scientific and engineering efforts in history. At its peak, more than 130,000 people worked on the project, not just physicists, chemists, engineers, mathematicians, construction workers, soldiers, electricians, machinists, secretaries. Entire towns were built almost overnight. Factories appeared in places where only empty fields had existed months earlier. The project eventually stretched across more than 30 major sites throughout the United States and Canada. Everything was hidden behind extraordinary secrecy. Workers often knew only the small task directly in front of them. Someone operating machinery in Tennessee had no idea what scientists in New Mexico were building. A technician enriching uranium might never meet the people designing the bomb itself. Many employees did not even know what the project's final goal was until after the war ended. By the time it was finished, the Manhattan Project had cost nearly $2 billion. In today's money, that would equal tens of billions. No nation had ever invested so much into a single scientific effort. The heart of the project stood high in the mountains of northern New Mexico. Officially, it barely existed. Maps showed little. Roads ended at guarded checkpoints. Letters were carefully censored. Visitors were almost non-existent. This hidden community was called Los Alamos. Families arrived without fully understanding why they had been sent there. Children attended schools surrounded by military police. Scientists lived in simple wooden houses. The roads were dusty. The winters were cold. The isolation was complete. Yet within this quiet mountain town, some of the greatest scientific minds of the 20th century worked side by side. Enrico Fermi, Richard Feynman, Hans Bethe, Edward Teller, John von Neumann. Many had escaped Europe only a few years earlier. Now they found themselves working together on a problem unlike any in history. How do you build a weapon powered by the nucleus of an atom? Leading them was a man unlike anyone expected. His name was J. Robert Oppenheimer. He wasn't the oldest physicist, nor the most famous. He had never managed a project anywhere near this scale. Friends described him as brilliant, intensely curious, and capable of discussing quantum mechanics one moment and ancient Sanskrit literature the next. He spoke several languages. He loved poetry. He quoted philosophy from memory. At first glance, he hardly seemed like the person who should direct a military weapons program. Yet, General Leslie Groves, the officer placed in charge of the Manhattan Project, saw something unusual in Oppenheimer. He could bring extraordinary people together. He understood both theoretical physics and practical engineering. Perhaps most importantly, other scientists trusted him. Under Oppenheimer's leadership, Los Alamos became something remarkable. Competition disappeared. Ideas moved freely. Physicists argued late into the night, filling blackboards with equations before testing them. In laboratories, the next morning, every calculation mattered. Every mistake could cost months of work or thousands of lives. The greatest challenge was not proving that an atomic bomb could work. The science already suggested it could. The challenge was building one before Nazi Germany did. Time became the project's most valuable resource. Every passing month increased the pressure. Rumors constantly circulated about Germany's own nuclear program. No one knew how close Hitler's scientists might be. Perhaps they were years behind. Perhaps they were only weeks away. No one could be certain. That uncertainty drove the Manhattan Project forward at an extraordinary pace. Factories operated day and night. New technologies were invented almost as quickly as new problems appeared. Engineers developed methods for separating uranium-235 from ordinary uranium, an immensely difficult task because the two forms were chemically identical. Elsewhere, entirely new reactors produced another material that barely existed in nature: plutonium. It too could fuel an atomic weapon. For the first time, physics had become an industrial enterprise. Scientific discovery was no longer confined to university laboratories. It required entire cities, entire supply chains, entire industries, all focused on unlocking the energy hidden inside the atom. As 1944 turned into 1945, the scientists of Los Alamos could feel history approaching. The designs were nearly complete. The calculations had been checked again and again. Soon, there would come a moment when mathematics would no longer be enough. The theories born in Einstein's equations. The discovery made by Hahn, Strassmann, Meitner, and Frisch. The first controlled chain reaction, achieved by Enrico Fermi. All of it would face a single question: would it actually work? In an empty stretch of desert in southern New Mexico, workers quietly prepared a test site. A steel tower rose above the sand. On the morning of July 16, 1945, before dawn broke over the Jornada del Muerto, the journey of the dead man, the world witnessed something it had never seen before. A light brighter than the rising sun, a fireball, born not from chemistry, but from the heart of the atom itself. Robert Oppenheimer watched it climb into the sky and thought of a line from the Bhagavad Gita, a text he had studied for years. Now I am become death, the destroyer of worlds. 3 weeks later, that same energy would fall on a city in Japan, then another. The war the letter on Long Island had tried to prevent would end with the very weapon it had helped create. The fireball over Hiroshima lasted only seconds. Its consequences would last generations. 3 weeks after Trinity, the world watched a single bomb erase most of a city. Then, 3 days later, it watched a second bomb do the same to Nagasaki. The Second World War ended almost immediately after. For the first time in human history, people understood that the energy hidden inside the atom could destroy an entire city in an instant. But as the war faded and the shock slowly settled, a strange question began to take root in the minds of the very scientists who had built the weapon. What if the atom could do something else? What if this same energy, the one that had just leveled 2 cities, could be turned towards something entirely different? Not to destroy, to power. The idea wasn't new. Even before the war, Enrico Fermi believed nuclear chain reactions could be controlled rather than unleashed all at once. Chicago Pile 1 had already proven exactly that. Back in that quiet squash court in 1942, an atomic bomb releases nearly all its energy in less than a millionth of a second. A reactor could, in theory, release the same energy gradually, one atom splitting, then another, millions of times every second, but never all at once. It is the difference between burning every log in a fireplace simultaneously or feeding them into the fire one by one throughout the night. The energy is identical. Only the rate of release changes. If engineers could master that process safely, the atom might become one of the greatest sources of electricity the world had ever known. The years immediately following the war were filled with a kind of feverish optimism, almost impossible to imagine today. Across America, Britain, Canada, France, and the Soviet Union, scientists who had spent years building weapons suddenly redirected their attention toward peaceful applications. Governments funded new laboratories. Universities created entire departments dedicated to nuclear engineering. Industries formed around an idea that had barely existed a decade earlier. Nuclear power, to many people, it seemed like the next great technological revolution. Coal had powered the 19th century. Oil had transformed the 20th. Perhaps uranium would power everything that came next. Here's a simple fact worth remembering. Before any of the engineering details matter, a reactor doesn't create energy. Neither does coal, nor natural gas, nor gasoline. Every power plant on Earth simply converts one form of energy into another. A coal plant burns fuel to produce heat. That heat boils water. The water becomes steam. The steam spins a turbine. The turbine turns a generator. The generator produces electricity. A nuclear power plant follows almost exactly the same process. The only difference is where the heat comes from. Instead of burning coal, it comes from splitting uranium atoms. Those enormous cooling towers people associate with nuclear plants aren't releasing radiation into the sky. They're releasing ordinary water vapor, the same thing rising off a boiling kettle, just on a much larger scale. The real challenge wasn't the concept. It was building something reliable enough to run every single day for years without failure. The first breakthrough came quietly, almost invisibly, on December 20, 1951. At the experimental breeder reactor number 1 in the Idaho desert, a small team of engineers connected their reactor to a generator for the first time. The electricity produced wasn't enough to power a town. It wasn't even enough to power a single street. It lit 4 ordinary light bulbs, 4 small, glowing filaments in an empty stretch of desert. And yet, those 4 light bulbs represented something the human species had never accomplished before. For the first time in history, electricity had been generated directly from the energy inside an atom. Barely anyone outside the scientific community noticed. Newspapers were far more interested in weapons than light bulbs. But historians now recognize this modest, almost anticlimactic moment as one of the true turning points in the history of energy. It proved the concept was real. The atom could do more than destroy. It could provide. 3 years later, a second milestone arrived, this time with far more fanfare. On December 27, 1954, in the small Russian town of Obninsk, southwest of Moscow, the Soviet Union connected the world's first nuclear power plant to a functioning commercial electrical grid. Unlike the experiment in Idaho, Obninsk supplied real electricity to real homes. The amount was modest by today's standards. But the message was unmistakable. Nuclear power could become part of everyday life. Homes, schools, factories, hospitals, all powered by the same physics that had once flattened Hiroshima. The Cold War had already begun, and it quickly became clear that nuclear power wasn't just an energy story. It was a battlefield for prestige. Both superpowers wanted the world to see that their political system, their scientists, their engineers could deliver the future first. Britain accelerated its own program in response. In 1956, Calder Hall opened in Cumbria, becoming the first nuclear power station, built on a true industrial scale. Thousands of British homes soon received electricity generated from controlled nuclear reactions. Newspapers described it with genuine excitement, as though the future had arrived slightly ahead of schedule. America followed close behind. In 1958, the Shippingport Atomic Power Station in Pennsylvania began commercial operation, the first full-scale nuclear plant in the United States, built specifically to supply civilian electricity. Engineers everywhere watched closely. Governments watched even more closely. If these plants succeeded, the entire global energy landscape could shift, and, for a while, it looked as though it might. Magazines printed colorful illustrations of cities powered entirely by the atom. Architects sketched nuclear-powered neighborhoods. Engineers seriously proposed nuclear-powered cargo ships, nuclear-powered aircraft, even nuclear-powered automobiles. Some of these ideas were realistic, many were wildly ambitious, but they all reflected one shared belief that the atom was about to solve humanity's energy problems permanently. A single phrase captured the mood of the era perfectly. Electricity, some scientists predicted, would soon become too cheap to meter. So abundant, so inexpensive, that tracking individual household usage might no longer even be worth the trouble. Looking back, the prediction sounds almost naive, but at the time, it wasn't a fringe idea. Respected physicists genuinely believed it because the raw numbers seemed to support it. A single pellet of nuclear fuel, no larger than the tip of a finger, could produce roughly as much energy as several tons of coal. Fuel transportation became dramatically simpler. Power plants needed far less raw material by weight. For countries with limited access to fossil fuels, nuclear energy looked almost miraculous. The benefits reached beyond civilian electricity, too. Nuclear reactors began powering submarines. Traditional diesel submarines needed regular access to air, forcing them to surface constantly and exposing them to detection. Nuclear-powered submarines changed that equation entirely. Their reactors could run for years without refueling. Instead of surfacing every few days, they could remain submerged for months at a time. The world's oceans, strategically speaking, suddenly became much smaller. Aircraft carriers adopted the same nuclear propulsion soon after. Enormous ships, capable of circling the globe without ever needing to refuel. The very discovery that had produced atomic weapons was now reshaping naval power in ways few had predicted just a decade earlier. Yet beneath all that optimism, the most careful engineers never forgot one uncomfortable truth. The atom hadn't changed. It remained exactly as powerful as it had been inside the Manhattan Project. The only real difference was human control. Thousands of precisely engineered systems, all working together in perfect coordination. Cooling systems, control rods, pressure vessels, backup generators, endless safety procedures, rehearsed and re-rehearsed. Operators understood, at least in theory, that releasing this energy slowly demanded constant, unbroken attention. A reactor wasn't like a fire in a fireplace that could simply be left to burn down and go out on its own. Its power demanded responsibility, every hour, every shift, without exception. For years, that responsibility seemed entirely manageable. Reactors ran, cities lit up, confidence grew steadily. Around the world, governments began announcing ambitious plans for dozens, then hundreds, of new nuclear plants. To many observers in the late 1950s, it genuinely seemed like only a matter of time before nearly every industrialized nation ran on atomic power. The future looked bright, clean, modern, almost limitless. But history has an uncomfortable habit of reminding humanity that every technology powerful enough to save can also be powerful enough to destroy. Not through malice, but through a single overlooked mistake, a forgotten valve, a moment of carelessness inside a control room. The dream of unlimited, effortless atomic power was about to meet its harshest tests. Not in a laboratory this time, but inside real power plants, operated by real people, where small failures would eventually grow into disasters the entire world would remember by name. Strip away the politics for a moment. Strip away the fear, the Cold War competition, the glossy magazine covers promising cities powered entirely by the atom. Underneath all of that noise sits a machine. And the machine itself is easier to understand than most people expect. At the heart of every nuclear power plant is something called the reactor core. Inside that core sit thousands of long metal tubes, each one packed with small ceramic pellets of uranium, each pellet roughly the size of a fingertip. Stack enough of these pellets end to end, seal them inside a tube, and you have what engineers call a fuel rod. Bundle several hundred fuel rods together, and you have a fuel assembly. A typical reactor contains dozens of these assemblies, arranged with extraordinary precision, submerged entirely in water. This is where everything happens. Remember the chain reaction Meitner and Frisch worked out on that log in the snow. Remember the 28 minutes Fermi ran inside a converted squash court in 1942. The physics inside a modern reactor core is exactly the same physics, just running continuously, day after day, year after year, instead of for half an hour under a football stadium. A neutron strikes a uranium-235 atom. The atom splits. The split releases energy, and it releases more neutrons. Those neutrons go on to strike other uranium atoms, which split, releasing still more neutrons. Each step triggers the next. Each split makes the next split slightly more likely. Left completely alone, this process would either die out or run away entirely, accelerating faster and faster, until it became something no one could safely manage. So engineers control it using 3 separate tools, and each one plays a distinct role. The first is the moderator. Neutrons released by a splitting uranium atom move extremely fast. So fast that they're actually less likely to trigger the next fission event, not more. A moderator, usually ordinary water or sometimes graphite, slows these neutrons down as they pass through it. Counterintuitively, slower neutrons are far more effective at splitting the next atom than fast ones. Water does double duty here. It moderates the reaction and, as we'll see in a moment, also carries away the heat. The second is the control rod. These are the direct engineering descendants of the cadmium-filled buckets that hung above Fermi's reactor, ready to be poured if the chain reaction ran away. Modern control rods are made of materials like boron or cadmium, both of which are extremely good at absorbing neutrons before those neutrons can strike anything else. Slide the rods deeper into the core, and more neutrons get absorbed, so the reaction slows. Pull the rods out, and the reaction speeds back up. It's a remarkably simple mechanical solution to a process that's anything but simple at the atomic scale. Essentially, a dimmer switch for a chain. Reaction. The third is the coolant. Exciting atoms release an enormous amount of heat, and that heat has to go somewhere, or the fuel and the surrounding structure would rapidly overheat and fail. Water, or in some designs a pressurized gas, flows continuously through the reactor core, absorbing that heat and carrying it away. And this is where the actual electricity gets made. And it's a far less exotic process than most people imagine. In the most common design in the world, called a pressurized water reactor, water flowing directly through the core is kept under extreme pressure. That pressure is high enough that the water stays liquid even at temperatures well above its normal boiling point. Normally, water this hot would flash instantly into steam, but the pressure physically prevents that from happening. This superheated, pressurized water then flows into a separate, completely sealed loop, where it transfers its heat to a second body of water without ever mixing with it directly. That second loop of water boils. The steam it produces spins a turbine. The turbine spins a generator. The generator produces electricity. There's something worth pausing on here because it quietly answers one of the most common fears people have about nuclear plants. The radioactive water that actually passes through the reactor core never leaves the reactor building. It stays sealed inside its own closed loop for the entire life of the plant, transferring only heat, not radioactive material, to the water that eventually becomes the steam the turbine. The workers running the turbine hall are, in a very real sense, working with ordinary steam, generated by an extraordinary source. A second common design, called a boiling water reactor, simplifies this process slightly. Instead of using two separate loops, it allows the water inside the core itself to boil directly, sending that steam straight to the turbine. It's a more mechanically simple design, requiring fewer components, but it does mean the loop touching the turbine has come into closer contact with the fuel itself. Different countries adopted different designs for different reasons, some driven by physics, some by cost, some by whatever technology happened to be available first. But regardless of which specific design a plant uses, the underlying principle never changes. Stopped atoms, release heat, boil water, spin a turbine, generate electricity. It is, when you strip away the mystique, essentially the same idea a coal-fired power plant uses. The only real difference is the source of the fire. Which brings us to the question almost everyone eventually asks, usually with a slightly nervous tone. If a reactor is running an ongoing chain reaction, why doesn't it simply explode like a bomb? The answer comes down to a single concept: enrichment. Natural uranium, as it's mined from the ground, is made up almost entirely of an isotope called uranium-238, which doesn't split easily under normal conditions. Only a tiny fraction of natural uranium, less than 1%, is uranium-235, the isotope actually capable of sustaining a rapid, self-perpetuating chain reaction. Weapons-grade uranium is enriched until it contains roughly 90% uranium-235 or higher, concentrated enough that a chain reaction can occur almost instantaneously across the entire mass, releasing all its energy in a fraction of a second. Reactor fuel, by comparison, is enriched to only about 3 to 5% uranium-235. Think of it as the difference between a small splash of gasoline and an entire sealed barrel of it. Both will burn. Only one is capable of detonating. The chemistry, or in this case the physics, of the fuel itself makes an explosive chain reaction physically impossible inside a properly designed civilian reactor. The concentration of fissile material simply isn't high enough, and the geometry of the core isn't arranged to allow it. That doesn't mean a reactor is without risk. It simply means the risk takes a different shape than most people assume. What can go wrong inside a nuclear plant isn't a nuclear explosion in the sense people usually picture. It's a meltdown, a situation where heat inside the core builds up faster than the cooling systems can remove it, causing the fuel itself to overheat, warp, and, in the worst cases, breach its containment. That distinction between an explosion and a meltdown would matter enormously in the decades ahead, in ways the optimistic engineers of the 1950s hadn't yet been forced to fully confront. For most of the 1950s and well into the 1960s, though, the machines simply worked. Reactor after reactor came online. Electricity flowed steadily into homes in Pennsylvania, into towns across Cumbria, into the streets surrounding Obninsk. Engineers who had spent the war years building weapons now spent their careers calibrating control rods, monitoring coolant flow rates, and fine-tuning safety systems with almost obsessive attention to detail. The atom, tamed and deliberately slowed, was quietly lighting kitchens, powering factories, and running hospital equipment across 3 continents. For a while, it genuinely looked like the peaceful promise of the atom had been fulfilled almost exactly as its earliest champions had hoped. But taming something this powerful required constant, unbroken vigilance. Every valve mattered. Every gauge, every pump, every backup system had to function exactly as designed. Every single day, without exception, a nuclear reactor wasn't a machine you could build once and simply forget about. It demanded operators who understood completely exactly what was happening inside that steel vessel. Every second, every shift, for as long as the plant remained in operation. Most of the time, for most of the world, that vigilance held. But not everywhere, and not always. In the years ahead, 3 names would become permanently woven into the story of nuclear power: 3 Mile Island, Chernobyl, and Fukushima. Each one would teach the world something different about exactly what happens when the delicate balance between human control and atomic chaos tips, even briefly, in the wrong direction. By the late 1970s, nuclear power had become almost routine. Dozens of reactors hummed quietly across the United States, generating electricity with the kind of unremarkable reliability that made people stop thinking about them entirely. That quiet confidence was about to be tested for the first time in America on a spring morning in Pennsylvania, March 28, 1979. 3 Mile Island, a nuclear plant sitting on an island in the Susquehanna River just south of Harrisburg. At around 4 in the morning, a relatively minor mechanical failure occurred in the plant's cooling system. A stuck valve, the kind of small malfunction that engineers had planned for 100 times over. But a second problem compounded it almost immediately. A separate valve meant to relieve pressure opened correctly but then failed to close again. And critically, The control room's instruments didn't clearly show operators that it had stayed open. For the next several hours, operators believed they had too much water in the reactor system, when in reality they had far too little. Acting on that mistaken belief, they reduced the flow of cooling water even further, the exact opposite of what the situation required. Inside the reactor core, water levels dropped. The top of the fuel rods began to be exposed to steam instead of water. Without proper cooling, the fuel began to heat rapidly. Roughly half of the reactor core suffered damage. A portion of it partially melted. No one died. No one outside the plant received a dangerous dose of radiation. The containment building, exactly as designed, held. But the psychological damage was immense and immediate. News coverage speculated about a possible meltdown, reaching the ground beneath the plant, a scenario nicknamed the China Syndrome, after a film released just 12 days earlier that imagined exactly this kind of disaster. Tens of thousands of residents evacuated the surrounding area, uncertain whether they were in danger. In the aftermath, investigators traced the accident back to a combination of confusing control room design, inadequate operator training, and a safety culture that hadn't fully anticipated how multiple small failures could compound into something serious. No new nuclear plant construction permits would be approved in the United States for more than 3 decades afterward. 3 Mile Island didn't kill anyone directly, but it effectively froze an entire industry. 7 years later, on the other side of the world, a far more serious accident would show the world what happens when warning signs like these are ignored rather than heeded. April 26, 1986. Reactor number 4 at the Chernobyl nuclear power plant. In what was then the Soviet Union, now Ukraine, plant operators were running a late-night safety test designed to check whether the reactor's turbines could continue generating enough electricity to power emergency cooling pumps during a power outage even after the main steam supply had been cut off. It was the kind of test that should have been routine, but the reactor itself carried a fatal design flaw, one that Soviet engineers understood only imperfectly at the time. Unlike most Western reactor designs, Chernobyl's RBMK reactor became more unstable, not less, as its power output dropped to very low levels, a strange, dangerous quirk in how its graphite moderator and control rods interacted with the fuel. To make matters worse, in preparing for the test, operators had disabled several of the reactor's automatic safety systems, believing they might interfere with the experiment. Emergency cooling systems that should have caught early warning signs were switched off at 1:23 in the morning as operators tried to shut the reactor down as part of the test sequence. The reaction that was supposed to be dying out instead began to surge. Power output spiked far beyond anything the reactor was designed to handle, reportedly to roughly 100 times its normal operating level. In a matter of seconds, steam pressure inside the reactor built explosively. A massive steam explosion tore through the reactor building, blowing the 1,000-ton steel and concrete lid clean off the reactor. A second explosion followed almost immediately, likely triggered by hydrogen gas that had built up inside. The reactor's graphite moderator, now exposed directly to open air, caught fire. For the next 10 days, that fire burned, releasing a plume of radioactive material directly into the atmosphere. Winds carried radioactive fallout across Ukraine, Belarus, and Russia, and eventually across much of Europe as far as Scandinavia and the United Kingdom. Firefighters and plant workers rushed toward the burning reactor with almost no understanding of the radiation levels they were walking into. Many received fatal doses within minutes. 31 people died in the immediate aftermath, mostly firefighters and plant staff. The long-term death toll, tied to cancers and other radiation-related illness across the surrounding region, remains fiercely debated among scientists to this day, with estimates ranging from the low thousands to considerably higher. An area roughly 19 miles in every direction from the reactor was declared an exclusion zone. More than 100,000 people were evacuated, many of them permanently, leaving behind entire towns exactly as they stood on the night of the accident. Pripyat, the town built specifically to house Chernobyl's plant workers and their families, still stands abandoned today. A frozen snapshot of Soviet life in 1986, slowly being reclaimed by forest. The exclusion zone remains largely uninhabitable for humans even now, 4 decades later. Though wildlife has returned in surprising numbers, thriving in the near-total absence of human activity, Soviet authorities initially tried to suppress news of the disaster entirely. It was only after radiation sensors in Sweden detected unusually high readings 2 days after the explosion that the world began to understand something catastrophic had occurred behind the Iron Curtain. The delayed, incomplete information released by Soviet officials would later be cited as one of the clearest early symptoms of a system beginning to lose the trust of its own citizens. Some historians consider Chernobyl's mishandling a genuine contributing factor to the eventual collapse of the Soviet Union itself. Just 5 years later, 2 accidents, 2 different reactors built on 2 different continents under 2 very different political systems. And yet, looking at them side by side, they share a single uncomfortable lesson. 3 Mile Island failed because of confusing instruments and a series of small human misjudgments, compounding under pressure inside a reactor whose fundamental design remained sound throughout. Chernobyl failed because of a flawed reactor design, disabled safety systems, and a culture that prioritized completing a test over questioning whether that test should be run at all. In both cases, the atom itself hadn't changed. It performed exactly as physics predicted it would, obeying the same rules Fermi had proven controllable back in that squash court in 1942. What changed was the margin for human error. How much room a given design and a given set of decisions left for mistakes before those mistakes became irreversible. Nuclear power's harshest critics point to Chernobyl as proof that the technology is simply too dangerous to trust at scale. Its defenders point to the same accident as proof of exactly the opposite, that a fundamentally different design, with fewer inherent flaws and better safety culture, would never have failed in the same way. Western-style reactors, they note, have never suffered an accident remotely close to Chernobyl in scale. Both arguments would resurface with new intensity 25 years later, this time not because of a design flaw or a mishandled safety test, but because of something no engineer could fully plan for: the raw, overwhelming force of nature itself. By 2011, the nuclear industry had spent 25 years trying to move past Chernobyl. New reactor designs emphasized redundancy, layered safety systems, and containment structures built to withstand almost any conceivable failure. Japan, in particular, prided itself on some of the most rigorously engineered nuclear infrastructure on Earth. Then the ground itself decided to test that confidence. March 11, 2011, 2:46 in the afternoon, local time. Off the northeastern coast of Japan, the ocean floor ruptured along a fault line, releasing a magnitude 9.0 earthquake, one of the most powerful ever recorded and the most powerful in Japan's documented history. At the Fukushima Daiichi nuclear power plant, on the coast of Fukushima Prefecture, the earthquake itself was handled almost exactly as designed. Sensors detected the shaking immediately. Control rods automatically inserted into all 3 operating reactors within seconds, shutting down the chain reaction almost instantly. Backup diesel generators kicked in smoothly, ready to keep cooling systems running. Now that the plant was disconnected from the earthquake-damaged electrical grid, for a few minutes, it looked like the system had worked exactly as intended. Then came the wave. Roughly 50 minutes after the earthquake, a tsunami generated by the same seismic event struck the coastline. At Fukushima Daiichi, the wave crested at over 40 feet, dramatically higher than the plant's seawall, which had been built to withstand waves less than half that height. Seawater surged over the wall and flooded the plant's lower levels, where the emergency diesel generators were housed. Within minutes, those generators were submerged and disabled. The reactors, though safely shut down, still needed active cooling. Residual heat from the recently halted chain reaction continues generating significant warmth for days after shutdown, and without power to run the cooling pumps, that heat had nowhere to go. Operators fought for hours using whatever backup measures remained, including car batteries scavenged from the plant's parking lot, trying to keep enough instrumentation running to understand what was happening inside reactors they could no longer properly cool. It wasn't enough. Over the following days, fuel inside 3 of the plant's reactors overheated and partially melted. Hydrogen gas, produced as overheating fuel, reacted with the water and steam around it, built up inside the reactor buildings. On March 12th, and again over the following days, that hydrogen ignited, causing a series of explosions that blew apart the outer structures of several reactor buildings, though the primary containment vessels themselves largely held. Radioactive material escaped into the surrounding air and, in smaller amounts, into the Pacific Ocean. Roughly 150,000 people were evacuated from the surrounding area, some permanently. Unlike Chernobyl, there were no direct deaths from the reactor accident itself. The earthquake and tsunami, by contrast, killed nearly 20,000 people across the region, almost entirely from the wave itself, not the nuclear incident that followed it. That distinction is often lost in how the disaster gets remembered. Clean and decommissioning work at Fukushima. Daiichi continues today, more than a decade later, and is expected to stretch on for decades more. Japan has slowly, carefully begun releasing treated wastewater from the site into the ocean under international monitoring, a process that remains controversial with fishing communities and neighboring countries alike. Fukushima reshaped the global nuclear conversation almost overnight. Germany, watching the disaster unfold, announced it would phase out nuclear power entirely. Accelera shutdown that has since removed nuclear energy almost completely from its national grid. Several other countries paused or scaled back their own nuclear ambitions in the months that followed. France, meanwhile, chose the opposite path, already generating around 70% of its electricity from nuclear power. France doubled down, treating its decades of operational experience as evidence that the technology, properly managed, remained safe and necessary. The United States found itself caught in the middle, neither abandoning nuclear power nor meaningfully expanding it. Existing reactors, continuing to run for years, sometimes decades, past their original planned retirement dates, while new construction remained rare and expensive. For years, that stalemate held. Then the terms of the debate began shifting again, this time driven less by fear of accidents and more by an entirely different kind of crisis: climate change. As the urgency around reducing carbon emissions intensified through the 2010s and into the 2020s, a curious realignment began among people who had spent decades opposing nuclear power on environmental grounds. Solar and wind power had grown remarkably cheap and increasingly widespread, but they came with an unavoidable limitation: both depend on weather and time of day, and storing electricity at the scale needed to smooth out those gaps remained, and still remains, an unsolved engineering challenge at a global level. Nuclear power, whatever its risk, produces virtually no carbon emissions during operation and generates electricity continuously, regardless of weather, season, or time of day. A growing number of environmentalists and climate scientists, some of whom had spent entire careers opposing nuclear energy, began quietly reconsidering their position. Several prominent voices in the climate movement now argue that abandoning nuclear power in the face of an accelerating climate crisis may end up causing far more harm than any nuclear accident realistically could. Critics push back just as firmly. Nuclear plants remain enormously expensive and slow to build, often taking a decade or more from approval to operation. Time the world may not have if climate targets are to be met on schedule. The question of what to do with long-lived radioactive waste remains unresolved in most countries. And while accidents are rare, Chernobyl and Fukushima demonstrated that when something does go wrong, the consequences can stretch across decades and, in some cases, across borders entirely. The debate, in other words, hasn't been settled. If anything, it has grown more urgent, more consequential, and more genuinely uncertain than at almost any point since those 4 light bulbs first flickered on in the Idaho desert in 1951. And yet, quietly, in laboratories far removed from any of these arguments about fission, scientists have spent decades chasing something else entirely, not the energy released when atoms split apart. The energy released when atoms are forced together. The same process that powers every star in the night sky. For most of that time, it remained purely theoretical. A promising idea always described as still decades away from working. That changed for the first time in human history on a December evening in 2022. Everything we've covered tonight: Fermi's squash court, Meitner's walk in the snow, Oppenheimer's fireball in the desert, Chernobyl, Fukushima, all of it has been fission. Splitting atoms apart, the sun does the opposite. Deep inside its core, under pressure and heat almost impossible to describe, hydrogen atoms don't split. They're forced together. Fusion. 2 light nuclei crash into one another with such force that they merge into something heavier, helium, and in that merging, they release energy on a scale that makes fission look almost modest by comparison. This is the same reaction lighting every star in the sky above you right now. For decades, physicists have understood fusion perfectly well in theory. The equations aren't controversial. The energy is real. And unlike fission, fusion produces no long-lived radioactive waste, carries no risk of meltdown, and runs on hydrogen, an element so abundant it can be extracted, in practice, from ordinary seawater. If fission was humanity learning to tame a wildfire, fusion is humanity learning to build a small, private star. The problem was never the physics. The problem was recreating the conditions of a star's core here on Earth, without a star's gravity to hold everything together. Scientists have been chasing controlled fusion since the 1950s, and for just as long, a tired joke followed the field everywhere it went. fusion is 30 years away, and it always will be. Then, on the evening of December 5th, 2022, at the National Ignition Facility in California, something happened that had never happened before, anywhere. In the history of our species, 192 lasers, all firing in perfect unison, converged on a fuel pellet smaller than a peppercorn. For a fraction of a second, that tiny pellet reached conditions hotter than the center of the sun, and for the first time ever, the fusion reaction inside it produced more energy than the lasers had used to trigger it. Scientists call this moment ignition. It wasn't a power plant. It wasn't ready to light a single home, let alone a city. But it was proof, undeniable, measurable proof, that the door humanity had been pushing against since the 1950s had finally, just barely, cracked open. The story that began in a squash court in 1942 with 3 men and 3 buckets has never really been about one discovery. It has been 80 years of humanity slowly learning to hold something impossibly powerful in careful, trembling hands, sometimes succeeding beautifully, sometimes failing in ways the world will never forget. The atom hasn't changed since Fermi first split it. It never will. What keeps changing is us, our understanding, our caution, our ambition to reach for the same fire that lights every star and hold it here safely on Earth. The energy that powers the sun may, one day soon, power your home. That story isn't finished. It's only just beginning. And if you want to be there for the next chapter, the way to make sure you don't miss it is simple. If tonight's journey helped you drift off, hit like before you go. It genuinely helps this channel keep making these for you. If something in here stayed with you, a moment, a name, a number that surprised you, drop it in the comments. Nothing helps more than hearing what you took from it. And if you know someone who'd fall asleep to this too, someone who loves history or physics or just needs a calm voice to end their night, share this with them. The sleeps well. And I'll see you in the next one.